at the first. Okay. So this talk is about numerical MPC for systems with state-dependent jumps and discrete actuators. And we want now to focus on non-differentiable right-hand sides. So we have a differential equation, but it's actually not really a differential equation because it has a possibly jumping right-hand side. So the easiest case is what we call NSD1, the first level of non-smooth dynamics. And there we would just say the system itself is not differentiable. I mean, the right-hand side is not differentiable. That still means that the x dot is well defined as a function. For example, we could have this x dot equals 1 plus the absolute value of x. And here you see that the trajectories would still look like decent differentiable trajectories. That's what is visualized here on the left. So there's no conceptual difficulty with that. It's just numerically destroying the order of our integration method. And so we would somehow like to treat that better by either smoothing. That's one standard way here. You just smooth it away. It's not the most efficient way. I think more efficient would be to use some of the methods for the next smoothest level that we explain in this talk and apply them also to this level. Yeah? Then you could retain the high integration order. But NSD2 is already creating a lot of difficulties. Yeah? So the second level makes a jump in the right-hand side. That means actually that its derivative is different on the left and on the right on the point where the jump occurs. For example, look at the example x dot equals 2 minus the sine of x, which jumps from minus to plus 1. So this is not even differentiable. It's not even continuous as a function, right? And so that means that x dot is actually jumping. And in the trajectory, this appears like a kink. This is conceptually a problem for derivatives, right? So how is x dot, is it actually a differential equation? But it's not so much a difficulty because you could, so to say, think of the first piece pasted together with the second piece. So one can actually define generalized solutions of these differential equations. But numerically still it's a strong nonlinearity that's difficult to treat. And I should say that there's a similar case, but it's also different, and that is when you have external switches by discrete actuators. So these are also a very strong source of, let's say, non-convexity. But if you think of them, they are different because we can decide when the switch would happen. Yeah? So you could just, I mean, I can decide when to switch on and off the light in this room, and it will change the dynamics maybe, I mean, of your attention. If I switch it on, you might immediately get a boost. If I switch it off, immediately you might get lower, but I would decide when to switch it on and off, right? This is different when there is like a state-dependent jump, which could appear, for example, a state-dependent switch when you have something like a safety valve opening if some pressure gets too high or whatever, right? So NSD3, our third level, that's the most difficult class. These are state-dependent jumps, and they appear in some systems where you have, for example, direct jumps in the change of the velocity. For example, if I take a ball and I think of basketball, right? What you do when you play basketball, you have a ball, you throw it to the ground, and it jumps up. And it jumps up immediately. I mean, at least if you want to model it as a rigid body, then it would just, at the moment that it touches the ground with a certain speed, it would change the speed to upwards, right? There is a jump in the speed, which is a state of our system, and then the ball moves upwards. So you see there is actually a real jump in our system, and this jump is completely extending the concept of differential equation. You can still somehow maybe write a simulation routine that says if you if you touch the ground and if you have a speed down into the down direction, then immediately change the speed to positive and go on. And then so you could in theory write a simulator for that, but it will be not an integration method actually. Yeah? So it's somehow getting out of the domain of differentiable optimization and also of ODE simulation. I want to give you an example of such systems. This is level 2, NSD2, so a simple example. So let's imagine that you want to follow a sinusoidal reference that's happening actually in power converters very often. You have a photovoltaic system and it's creating direct current that you need to then bring to a high level and to sinusoidal form in order to put it into the grid. That's a DC-AC power converter, and this is work by Benjamin Stickern, a PhD student I supervise academically, who is employee at the Fraunhofer ISE, and Gianluca Frison, who is a team member. And so now we want to, in particular, react very fast to grid failures, which are nasty things that happen sometimes. And that at that moment, your power converter, so to say, needs to really do the right decisions in order to not explode. In the model that Benjamin developed, he has just 3 states, so relatively simple. It's even linear in the states. Yeah? And then he has one binary input, which is actually a switch. I don't go into the details here. And then there is one interesting other thing that's a state-dependent switch, which is due to diodes, which are, so to say, safety valves, but for electronics. So a diode here will actually let current through only in one direction. And so it depends on when you switch, so to say, one switch off, there is still a diode that might either let the current through or not. And there is typically a state-dependent switch in this so-called blanking time. And at the end, we want to have a sampling time of 25 microseconds, quite fast, and a short prediction horizon just of 2 sampling times. That's what Benjamin aims at, and he is nearly there, but not yet at the experiment. But what they needed to really make this whole thing work is hand-tailored methods. So you wouldn't take any of the ready-made software, I mean, pieces of it and ideas of it, but then you just hand code your Euler integrator and your Runge-Kutta integrator. Actually, there are some Euler steps in these blanking times because they are so short that this turns out to be the cheapest here. And for the longer parts of these switches, I mean, there's always switch on and off in each of these 25 microseconds. So there's like for off, you have a Runge-Kutta step. For on, you have a Runge-Kutta step. In between, there are these blanking times. There you do 2 Euler steps, and that's it. And then he did a hand-tailored real-time algorithm on this and is, I think, on track to do this on the industrial photovoltaic power converter in an industrial project. So just to give you a bit of motivation, what's interesting to us. The overall talk is structured in the following way. I want to first go into the non-convex modeling concept that is actually in form of complementarity constraints. I think that's a very powerful thing and allows me to embrace the non-convex now, which is something that we didn't do so far. Usually we try to do as convex as possible every formulation, but here we really go into the non-convex world. And there actually I recommend to keep, let's say, the non-smoothness explicit, yeah? Not hide it by smoothing. A second part of this talk is about finite elements with switch detection. It's a new idea that I should actually give credits. I didn't do that at the beginning to my collaborator, in particular Armin Nurkanovic, who developed that together with me and some others. We will then go into time freezing for state-dependent jumps, which is an idea which actually transforms this very non-smooth jumping level, NSD3, to NSD2. I hope that you will like that idea as much as I do. And at the very end, I want to still talk about a 3-step decomposition method for discrete actuators, which is a bit related, but it's a bit also different than the non-smooth dynamics, because as I said, we decide on the discrete actuators ourselves. So let's recall a bit what we do here, and I think it's also useful to do it in this course. We need to solve nonlinear programs, as you remember, by discretizing our continuous time NMPC problem, which I restate here on the left side. I use now the typical state dynamics with X and U, like we do in control engineering. Just relax and get used to that as well. It's good to know both notations. Typically, actually, the L function in this objective and the E function would be just convex, quadratic, or some other convex penalties. And also our constraints are typically convex. Yeah? And then the whole problem would be convex if the system F would be linear, but it isn't. Yeah? And the system F is nonlinear, and that makes the whole thing non-convex. So now we apply any of our preferred discretization methods. And if you go to the right side of this picture, we see now a discretized form of the problem before, and I introduced now extra variables that I call zk. I call them zk because they have some, let's say, they are different than the x and the u. They are, so to say, they are intermediate variables on each of these integration intervals. And you remember maybe from the second talk that we have these possibilities, so to say, to, for example, use Runge-Kutta methods. They will have lots of hidden variables, like all these intermediate steps, all these intermediate stages. All this together I call Z in this slide. Yeah? So in a fully simultaneous setting, I will actually just let the optimizer solve for them as well. So I will not even eliminate them in the simulation function, which we did until now. But a fully simultaneous way of thinking is that you even leave these exposed to the optimizer, right? So my optimizer has to solve the differential equation entirely. Yeah? This makes it even sparser, but also bigger. So all these Zs are now also part of the optimization problem here. And they might, because you can also impose constraints and intermediate time points, they might even influence our constraints. So now an interesting observation in MPC practice is that this phi function, phi L and E and the phi H, they still are convex typically if we started with convex ones. So you would have, for example, linear or quadratic, they would be linear or quadratic functions. And still the only nonlinearity and only non-convexity in the problem is in this differential and algebraic equations in the middle, phi f diff and phi f alg. Yeah, they are the non-convex part of our problem. And yeah, because the x is now the states, I summarize all variables in the vector that I call W now, right? So W is now all the optimization variables together. And now I'm back in the NLP world, safe. And what Newton-type methods do now is they generate a sequence of iterates in this big space W by linearizing and solving convex subproblems typically, right? And one method that we like a lot is the so-called sequential convex programming method, SCP, where we really strictly follow the philosophy that we only linearize what is non-convex, namely, in this case, the dynamics. So we just make the F linear by linearizing it. So if you look at the left, you have the summarized NLP here with convex function J, convex functions H, and then a nonlinear but differentiable function F in the middle. And then in this SCP method, sequential convex programming, you actually select the iterate, the next one, based on the current one by solving a convex subproblem, which we see here on the right. Please note that the only thing which has changed is the linearization of F. So we have F, L, the linearized, the Taylor series, at the point Fi was the current iterate. Yeah, so we take this linearization there in order to create a convex problem. That one we can solve reliably, for example, with the QP solver in most applications. And that gives us the next iterate in the whole trajectory space W. This works extremely well for mildly nonlinear systems, also in microsecond NMPC, and I cite here some papers I will put on the webpage. And now the question is of this talk, what would happen if we do have a significant non-convex structure in this problem? I mean, apart from this linearization, I mean, the nonlinearity of F, which I assume to be mild, let's say, right? So I can differentiate and then I still have a good approximation. But if it's significant, I would like to know it explicitly. And that's what we want to try to do now. So let's have a look at one really nice way to represent non-smoothness in optimization problems. And these are the so-called mathematical programs with complementarity constraints. So that's something I want to share with you. So that's a useful way to model non-smoothness. There are different others ones, but the main point is to make that explicit. And so I will use a very specific notation all the time, which is here at the top. X perpendicular to Y. It's a symbol that I apply to vectors. And that basically means that the scalar product between the two is 0. Yeah, that's what perpendicular means, right? And it's typically combined with the equality that one thing should be, both should be positive or non-negative at least. And that's what you see here on the left side at the bottom of our problem. So there is this constraint that says 0 should be smaller than L times W, and that should be perpendicular to R times W, and that should be bigger than 0. So these are, so to say, 3 conditions together on the vector of W's. And altogether, this is actually describing L-shaped sets. So I think let's look at the example on the right. It's a very simple toy example. You have a 2-dimensional search space here only. And if you look at the first component, x1 or w1, so here in the graph it's x1, you would see that it should be either 0 or it can be positive, right? The second component can also be 0 or positive, but once one of them is positive, the other needs to be 0. And that's why we have this L-shaped set here, which is our feasible set for that problem. The objective function itself is nice and convex and quadratic. And you see that it's it has a minimum at 1, 1. It has 2 local minimizers at the 2 points. I think I need to get my pointer back. It's a bit nasty. So I don't stop the recording, but I stop the way to present. Maybe I just go to full screen view. Maybe that's easier. I get rid of that here. And I move that to the might be some way to, let's maybe try once. Maybe I have it back. No, I don't. Okay. So I just work with this. Ah, that's a good idea. Maybe that's a nice idea. Thank you. I will use the one in Zoom. If I can find it without my mouse. I have no mouse. Ah, no, I somehow have it. Yeah, exactly. So, and then I do have a mouse, hopefully. Spotlight is, that's maybe what I need. I think I will better use the mouse. What a pain. Maybe draw. You know what? I will just.
There's somebody in the chat suggesting you have to press document in the top right corner.
For Zoom, you mean? Or for here? Ah, that's already good. Yeah, I think that is a way to go, let's say. Now I have, yeah, maybe I do it this way. Okay. Okay, maybe we try to do it this way. At least we can see most of the slide. Yeah.
One more question in the chat regarding the content.
Yes.
The question is whether both constraints can be active.
Yes, so both constraints can be active at the same time. I mean, let's say it is only one constraint, it's a complementarity constraint. So the question is if both can be active at the same time. Basically, this is the feasible set here, and here now with the mouse much better, I saw. And of course, both can be active at the same time, then we are at this corner point. And this is also the most complicated point because there's no constraint qualification, I mean, not in the traditional way that it's holding here. This point, in fact, turns out to be a local maximizer of that problem, right? Of this problem. Here's a minimizer, there's a minimizer, and there's a maximizer. So you see already from this fact that we have two local minimizers, right? It's definitely non-convex, despite the quadratic function, despite everything. And so where does the non-convexity come from? It's only this little sign here in the middle. Yeah, that's the only non-convexity. But non-smooth optimization immediately means no, not immediately. But if it's non-smooth constraints, yeah, then you immediately have non-convex optimization problems. So due to this complementarity constraint, you have an MPCC that is always non-smooth and non-convex, and that's a nasty combination, right? They are not nice, but there are ways to treat them, and you can treat them still with derivative-based methods, and that's what I want to share with you. I think one of the most successful methods is this penalty method, which generates a sequence of, let's say, optimizers. That's why I call them W0 star and W1 star. So these are actually solutions to optimization problems where you solve an NLP with increasing weights. So let's look at the left side. So on the left, we have this general form of a mathematical program with complementarity constraints, an MPCC. I actually separated this strong nonlinearity out by just having this product of the two vectors. I call this, I denote this by the function phi of w, right? So phi of w is this product that should be always zero. Yeah? This is a nasty constraint because if one of them, I mean, if both are zero, then there is no constraint qualification on this constraint, right? So I wouldn't want to formulate that as an NLP and give it to an NLP solver. They will typically not be very happy with that. What you do instead now is you put this phi into the objective and you penalize it. Very intuitive, yeah? The phi can never be negative because of these other two constraints, right? And these other two constraints I just keep in the problem. Yeah? So everything else is unchanged. I just moved the phi from being a constraint into a penalty. And I put this row bigger and bigger and bigger. And now the key is, again, as like in interior point methods, I will start with a small weight and then increase it consecutively. So you need now a good NLP solver to solve that. And I should say that this problem, even if you started with a QP, is now non-convex, yeah? Because this function phi is inherent. I mean, it's also non-convex. Yeah? It's a quadratic function, but it's non-convex. So the crucial part of this algorithm is you always start at the previous solution. So you take one iterate and then you initialize and go into the NLP solver with the next higher weight. And this method is obviously heuristic, like most of NLP solutions, right? I mean, you always find only local minimizers, but one can show, and that's what the papers here by Rife and Wright have shown, is that actually if your row is high enough and you find a complementarity solution, then this is in fact a solution to the original problem. And also if you have an original solution and you then initialize a problem with a high penalty, then it would stay at that solution. Yeah? So in that sense, your algorithm is able to basically solve this. Of course, it could still be that you get stuck in some other non-optimal points, maybe even in non-complementary points. But actually, yeah, if you find a solution with this method, it is a solution of the problem. And if you for some reason know a solution of your problem, it will be a fixed point of this algorithm. Yeah? So you can keep, you can stay at that solution. Good. So in principle, you can, so to say, you have a way to solve these things. But there's different ways to implement them. And I want to just give you the two algorithms that we use in the team. The first one is left. That's a generic penalty loop. And this generic penalty loop is exactly solving NLPs like I just described before. And these NLPs you would solve with a good NLP solver, for example, by IP-opt. Yeah, you could also use SQP methods, but yeah, at the moment we use mostly IP-opt here because it's good, has nice globalization, and is reliable, and exploits sparsity. So then you just increase rho, and then you have a solution after a while. Yeah? You can always use that method, but then you can do a bit faster for some special structure. And one of them is if you have a QP from the beginning, which just has this extra complementarity constraint. So it's not convex anymore because of the complementarity, but if you have a problem of that form, then the objective is now convex quadratic, right? The constraints are linear, maybe equalities, maybe inequalities, and then here's the complementarity part also in the objective, right? And then you increase rho. And this one you can solve with a method that, as I said, we call SCP, sequential convex programming, which in this context just turns out to be a little gradient adaptation. So you change the gradient while you iterate. And that allows us to hot start QP solvers. So basically we leverage online optimization techniques that have been originally developed for MPC, but here they are used in the homotopy method for LCQP, as we call them, linear complementarity constraint quadratic programs, LCQPs. Yeah? And that's the method that was implemented by Jonas Hall in his master thesis and afterwards. And that is now made openly available in this package that we call LCQP. And here is just one example on which he applied it. It's a continuous optimal control example, which is extremely simple. So maybe look a moment at the top problem. We have just a quadratic deviation of a single state from 0 and some terminal state that we want to hit at time horizon 0 to 2. And then we have a differential equation with this nasty state-dependent jump of non-smoothness level 2. We don't have a fixed initial value, so basically, and we don't have a control. So there is 1 degree of freedom in this problem, which is actually the initial value. That's it, right? Nothing else is really free. The rest you could eliminate. If you would do single shooting, you would just eliminate everything apart from x0. Okay, then we discretize that using implicit Euler with a step 2 divided by n. 2 is the time horizon, n is the number of steps, very simple. And after a little bit of logical reformulations, which I spare you, you can actually reformulate that whole thing into an MPCC. And that's what we have here at the bottom. And it turns out to be a linear complementarity QP. So we have state-dependent costs, which are quadratic, still the original ones, but I don't repeat them here, so I just summarize as E. And then we have the system dynamics constraints from the implicit Euler. Basically, yeah, you see implicit Euler, xk equals xk minus 1 plus h times something, and the something is now having a state yk, which is implicitly determined by these complementarity constraints. So there are 2 complementarity conditions, which basically model the switch. If you want, we can do that later on the blackboard, how to do this modeling. But basically, if you look at the top right here, this figure, that's the switch that we want to model. And you see there are 2 corners in that, right? That's the switch of the sine function. And because you have 2 corners, you need to basically have 2 complementarities. But they connect 1 variable, and y is actually the variable that's either 0 or 1. Yeah, so it can jump from 0 to 1. So now these methods that I just mentioned, they are penalizing, but there's some other methods that are relaxing. And so these relaxation methods, and then there are third methods that are smoothing. So you could do smoothing methods, you can do relaxation methods, and you can do penalization methods. And all 3 are penalized, compared here. And LCQP is based on this penalty method, as I said, right? But one interesting thing is if you look at the optimal solution to your problem, as a function of the initial value, x0, yeah, which, as I said, is really the only degree of freedom. If you make all other constraints feasible, yeah, then you have a deterministically defined trajectory. If you fix your discretization size, the problem with which we see here in yellow, that would be, so to say, the objective function as a function of our initial value, of our discretized problem. And this yellow line is non-smooth, nasty, really non-convex, non-smooth, really nasty, right? And it has lots of local minima, and they are in these corners. So this is not a nice problem, you see, right? you could just look at that plot and then you could say, and was my initial reaction like 2 years ago, no, let's forget about MPCCs. They are not good, right? They introduce lots of local minima. This is not good. Yeah? But then think twice and say, okay, but MPCCs, you solve them with these penalty methods. So in reality, actually, you have this homotopy. Yeah. So the truth is that you, on the path to your nasty non-smoothness, you have relatively smooth problems. And look at this blue line here at the bottom. That's what you get if you have a really smooth variation. Basically, if the penalty parameter is small, that's a relaxation. So you're always optimistic. You're too low, but you have a nice smooth function, and that is where you start your homotopy, yeah? With a low penalty, and then look at the red line. It's somewhere in between. The red line is already a bit closer, so to say. You have the increased penalty parameter. It's closer to the truth, actually. The true is here, the black line. That's the analytic solution of our ODE with a switch. But the analytic solution we don't have available because we have to discretize, right? So only for this test example, we know it. But you see that the blue line is similar in the sense that it's smooth, right? That's for a small parameter row. And then the red and the yellow, they are closer to the true one, yeah, because they are now not so relaxed anymore. They are closer, but they are getting non-smooth. So their derivatives are getting really bad. Yeah? So actually, that's roughly what happens in non-smooth optimization. You start with a small row. Your derivatives are correct, so to say, but you have a far too optimistic view of your optimization problem. Then you increase this penalty. Your view gets more realistic, but your derivatives get more wrong, but you don't, and you get lots of local minima potentially. But because you started nicely, you're guided, so to say, to get stuck in one of these good local minima. So it's a heuristic, but it allows you to solve some problems really nicely, avoiding combinatorial optimization. And then if you do also exploit the structure, that's what we do in this LCQP sure method, then you can get a solver that's about 2 or 3 times faster than others. For different discretization nodes, it was just tested on this example here. Okay, so this example tells you a lot. I think you can gain a lot of intuition about complementarity problems in optimal control with that. And so this is how these things can be solved. And so we shouldn't be too afraid of MPCCs in general. There's still this nasty thing that we have switches that we just don't detect, right? I mean, we had brutally discretized what we did now. And we know that an integrator that is, so to say, going over a non-smooth point will actually not perform very well. So the question is if we could alleviate things. And that's what we do with these finite elements with switch detection that Armin and I call FESD. And that's a method I want to share with you. It's yet in development. So this is not yet with a citable paper, unfortunately. But I think it's sometimes good to talk about these things already to get feedback and ideas and to help spreading them. So it's all about the second level of non-smoothness, which we also had just in the example before, which, as we just said, could be formulated by complementarity constraints. And that's what I want to do now. So let's first look at how this looks in state space. So think of a discontinuous right-hand side, which could be piecewise smooth on some disjoint open regions in state space, which I call Ri. So on each region, there is a nice differentiable dynamics, but between them, they can jump. And these boundaries are here the black lines. And we could express it this way by just saying F is Fi if X is in the region Ri, and yeah, in every region, a different one. But now if you want to numerically integrate that, our real aim would be that we should exactly detect the switching times. Why shouldn't the integrator, it should know that there is a switch, and we want to also obtain the right sensitivities across regions, which is lost in these brutal discretizations that I've shown before. And also we want to appropriately treat the evolution on the boundaries, and that's a more delicate point because actually we didn't define the F on the boundaries yet. But what would happen for a non-smooth dynamic system if you are, for example, simulating it across this boundary. So R2 and R1 are two regions. They have these vector fields pushing you to the boundary. What happens if you are on the boundary? Intuitively, you would say, hey, I get pushed from left, I get pushed from the right? I will just, and I get a bit of push along the boundary, so I will move on the boundary. And that's actually what would happen, right? If you think of it, that's the only sensible thing that should happen. If you would go to the right, really on the boundary, across out of the boundary, you would immediately be back. And if you do that on the left, you would immediately be back, right? And then you just move with the speed of the component that's along the trajectory on the boundary, you would move there. In fact, you could say, and that's one way to look at these systems, that they are infinitely stiff. Yeah, this is exactly, we talked about stiffness on Monday. This is, so to say, a system that's extremely pushed, so to say, on this manifold, namely infinitely strongly. And so basically this manifold becomes a kind of algebraic equation, and then you just move on this manifold. We call that a sliding mode, and there is a conceptually nice way to treat these, and that's called Filippov convexification, which I want to explain next. So Filippov's idea was that you replace the ODE, which isn't well defined for these jumping systems, actually by a differential inclusion. And this differential inclusion is actually using set-valued analysis. So you have an ODE that says the derivative x dot should be element in a set f. This little f of f, the little f here is for Filippov, right? So it's a set. And this set depends on my current state on my control, but it also depends on some, actually, no, the set doesn't depend, but the set is parameterized via some parameters that I call theta. And they are a convex combination of all possible systems. Yeah, so in theory, I have, so to say, in every state space region, I have all the f's available. I just add them up with the thetas. But the thetas should add to 1, so they must actually add to 1. Yeah? And they should all be positive. That means basically it's a convex combination of all f's, what I have here. But then the non-convex nasty constraint here, and that's important, of course, is the theta must be 0 if you're not in your region and not even on the boundary of your region. So when you're really a distance away from your region, then your theta must be 0 for that region. That means basically if you're inside a region, only one theta can be non-zero. But if you're at the boundary of two regions, two thetas can be non-zero. If you're at the boundary of 3 regions, which would be here a vertex, right? Of 4 regions even, then all these thetas could be non-zero. So that's basically the logic here of the Filippov convexification. And that is indeed a meaningful generalization of ODE to a non-smooth system with jumping, with switching dynamics. So for example, if we look at these two boundaries, so the closure of R1 and the closure of R2, if you intersect them, then you get this manifold here. And on this manifold, theta 1 and theta 2 can be non-zero. And in fact, these thetas will then become kind of algebraic variables, and they will just be chosen so that you stay on the manifold. That's what, so to say, will happen later automatically. So how do we compute these convex multipliers? And one way that is due to Stewart from a 1990 paper that Armin Nurkanovic and I like a lot. Armin discovered it and doesn't want to use other formulations for the sets anymore, which I agree. So there is a beautiful way to represent these sets by saying, I mean, you need some functions in order to describe them so that we can put it later into nonlinear optimization, right? So these sets are now defined by inequalities, and they are defined by actually functions that should be minimal on each region. So we have, so to say, each region has a function with the same index, right? And the region is defined all points where this function gi is smaller than all other functions gj. Yeah. So we basically choose our functions so that the minimum is in the region of interest. I mean, you can transform different formulations into different formulations, but this is like a nice one. If you choose this, then you can actually show that these multipliers theta, that so to say these convex multipliers, you can get them by basically solving a linear program, which so to say minimizes the sum of the g's weighted with the thetas. That's what we have here. Yeah, that's a linear program. For a fixed x, it's a linear program because theta are the optimization variables here. So if one of the g's is smaller than all the others, then the obvious solution to the LP is that you choose theta 1 for that one, because then this will minimize your objective, right? So if you look at this graph here, so there's the region boundary between R1 and R2. So if your G1 is smaller, then you're safely in region R1, and then this LP will push you to theta 1. That's 1. If you are on R2, then G2 is smaller, and then you will be pushed to that boundary by that LP. But if they are both equal, that means actually that you're on the boundary here, then theta 1 and theta 2 is unspecified, and there's lots of solutions for the LP. So if we now stay in the continuous world for a moment and we take this LP representation on the left that I have just introduced, I do a bit of shorthand of the notation, so stay on the left first. So I introduce a big F now, which is actually containing all my vector valued right-hand sides together, so that I can just have it as a matrix that I multiply with theta. That selects basically. It's like we had before with the parameter. It's a linear combination of all the thetas here. But then the theta is constrained to be in the set of optimal solutions of the LP. Yeah, really nasty object. We have also simplified notation by summarizing all the g's in one vector, right? G. And also the vector of all ones, I call it E here, and then I can express my, my simplex constraints here, that the theta is actually on the simplex by this simple expression here on the bottom left. So I can equivalently express that by optimality conditions, and that's where the complementarity system comes into play, because this LP, yeah, KKT conditions we discussed yesterday, just you introduce some extra multiplier we call lambda for these inequalities, and one that I call mu for the last equality, and then you add the gradient of these things together, and you set this gradient to 0. That's what this 1b is. You see the gradient G is the gradient of the objective, right? And then these are the gradients of the constraints. And then you have the complementarity condition here. And one interesting thing is that these equations 1b to 1d, and that's now interesting, they somehow implicitly, they are exactly 2m plus 1 conditions on the 2m plus 1 variables. Yeah, so m is the number of systems. We have, for each system, we have a theta. For each system, we have a lambda. And we have one mu. And the number of equations, 1b to 1d, is exactly the right number of equations. I mean, that doesn't mean that it's uniquely determining, and there are some corner cases where it doesn't. But in general, under some regularity, it's exactly the right number of equations for the unknowns. And now, you see, this is a well-defined ODE with some very nasty algebraic conditions. Yeah, so it's x dot is a function of all these thetas, and these thetas are uniquely determined by this set of equations below for a given x. So now you could do the conventional discretization. That's what we did before in this example that I've shown with these Euler. But you remember our discrete time Runge-Hutter discretization in the most general form, and here's the most general form for n time steps, and Runge-Hutter stages S here. Okay, S is now the number of stages. And on the left, I have the discrete time, the dynamic complementarity system in continuous time, and now I discretize that brutally, as I would say, by a Runge-Hutter method. Yeah? The brutal discretization just has all these algebraic conditions on every single Runge-Hutter stage. Yeah, that's these indices K and J. These are all the conditions here at the bottom. And then I have my Runge-Hutter conditions on the xkj and the vkj. You remember we had these velocity states to make it simple to make the connection. And we have here all our Runge-Hutter conditions. So I think when we are familiar with Runge-Kutta methods, we would accept that. It's an awful lot of equations, but the bottom line is this is nonlinear equations with complementarity constraints. So we could impose them as constraints in an NLP with complementarity constraints now. So let's do that. And in this case, it's just with fixed initial condition and without any optimization variables. So basically, it's a simulation problem. So you have an initial value fixed and then some system here. It's actually some form of oscillator that is either not an oscillator, and then you switch it on. And the switch appears when x1 changes sign. So you have a function g1, which is minus x. That's, so to say, going down, and the other one is going up. And they intersect at x1 equals 0, and that's actually where the switch appears. So if the variable x1, which is here in blue, this is the simulated trajectory, if it crosses 0, here is 0, at that moment you get the switch, and then your dynamics will change. What we see here in the is a bit nasty, and I better show it on the next plot. You can zoom in a bit here on the right. So what happens with our discretization method? Here we use a Runge-Kutta method, which is called Radau 2a collocation of 7th order. And this method actually represents our solution with polynomials, so it's nice for plotting also. So we plot actually on each Runge-Kutta step. Here's this nasty Runge-Kutta step. We can plot our what our Runge-Kutta method thinks our system to be. And so what happens here is that your trajectory is a nice smooth polynomial, while in reality, if you look at this dashed line, that would be the perfect solution to this non-smooth system. It would have the kink, obviously, because it switches. But this kink is very nastily and not very well represented by our polynomial, obviously. And so the question is, could we somehow ensure that the switches happen only at the element boundaries? That would be much nicer, right? Because then we are, I mean, an ODE solver is able to deal with switches that happen on the boundaries, because there is no need to have derivatives that are equal on left and right boundaries of an interval boundary. And that leads then to our idea of finite elements with switch detection. So in one line, I think, and I will probably not go into the details later. So I stay a bit longer with this slide, and then I jump over some others. So please be attentive for this slide, because that will be the explanation of the method. So this FESD method is a novel method for discretization of these dynamic complementarity systems, which is based on 3 ideas. And the first one is that we make the step sizes free. So that was something we usually fixed, right? But now the step size of each integration step is a free variable. But they need to add up to the total time, of course. Huh? We let the optimizer choose that. And then we allow the switches only at the element boundaries. So we somehow add extra complementarity constraints which ensure that they must switch at the boundaries, and they can never switch in the internal part of the interval. Yeah? So actually, that's what we impose. It cannot switch inside an interval. It cannot occur. And what we do here is we invented a kind of cross complementarities. So that's our name for that, that ensure that the boundary, that the switch cannot be in the interior. But then you could end up with solutions as we see it here in the middle. So there, the switch you see, I mean, the dashed lines are the element boundaries of these integration steps. It's nice in the sense that it detects this boundary, right? It's nasty because all the steps are of different size here. That's something you would typically not like, because it would allow your optimizer to play with your degrees of freedom, maybe increase numerical errors, just in order to get a better objective. And so what we try to get rid is this extra degree of freedom when we don't have a switch. So roughly speaking, what would you do in the perfect world? You would say, if I know where the switch is, I would just say, hey, all my elements before the switch have a variable size, because I need to detect the switch exactly. I cannot fix it, but they should be equal. And after the switch, they should also be equal, but they can be together, they can be variables. So they should just be equidistant, but the time, how much they are, can be still a degree of freedom. So that's what we impose. And we basically say the step size at one interval should be equal to the step size of the other interval but only if there is a jump, there is no need that they should be equal. So that's what we impose here. And we call that step equilibration. And that's actually helping you to avoid these additional degrees of freedom. And then this is, as I said, a bit nasty, and I will spare it to you, but with step equilibration, it gets even nastier. And then you have lots of conditions here. And you have lots of extra variables, in particular these step sizes. And maybe let me just look at the top line. So the step sizes, they need to add to 1, to t in this the whole time horizon. And then there is this red line here. You have the steps sizes of 2 subsequent intervals squared. They should be 0 if the function u is non-zero. Yeah? And this function u is even more complicated, so I spared. I call it Nurkanovic's indicator function. It's 1 if you do not have a switch. And it's 0 if there is a switch. And there could be lots of switches, unfortunately, because you can be, I mean, sorry, there can be lots of situations where it's really nasty and difficult to see if you're on a switch or not, because just saying I'm on the boundary between regions isn't enough. Because if you're also on these sliding modes, you don't have a switch. You are just on a sliding mode. You have a switch when you enter the sliding mode, and then you stay on the, when you exit it, you have another switch. So this is quite some intricate logic here, but it allows you to get the solutions that we just discussed before. Yeah, so maybe to give a bit of intuition, it's actually the multipliers lambda, they turn out to be continuous in time for these ODEs. And that's the key for the whole method, because we basically say these multipliers should be, they can only be non-zero if all the theta on the interval are 0. Yeah? And conversely, a theta can only be non-zero on an interval if all the multipliers on the interval are 0. And these conditions, which are just complementarity conditions of all thetas with all betas on the same interval, yeah, they lead to the fact that if you that a lambda at a boundary must be 0 if theta is either on the left or on the right non-zero. Yeah, because if it's on the left, it's non-zero, then your lambda on this boundary point must be 0, like on everything on this interval must be 0, but also on the boundary point. If it's on the other side, there's a theta that's non-zero, then all the lambdas right must be non-zero, must be 0, including the boundary point. So roughly speaking, the boundary point is constrained to be 0 in lambda if either left or right there's any theta that's non-zero. Yeah? And that allows us to basically restrict our switches to boundary points. Here's a simulation example, a really nasty system that at some point I think I gave it to Armin and said, try to simulate this system. And I think you could try to simulate that with smoothing methods. It's a really nasty system. It's an oscillator that's unstable. So you have a system dynamics that's spiraling out of 0. Slightly unstable oscillator, but it has also a switch. And the switch happens on this red manifold here, the circle. And there it switches just the orientation of your oscillator. So it's either, it's like a, so if you start here in the middle, that's your trajectory in blue, and then here the switch, and now you oscillate in the other direction. And that's the solution. And if you simulate that for 2 time steps, and you start at 1 over E, then you end at E. So Euler number. So you know the exact solution for that system. That's good for numerical comparisons, right? When we do these order plots and so on. Here's the correct solution. So change in the derivative of one of the 2 variables at that point. Actually, both would change in principle, but for this special trajectory, only one of them changes. Okay, let's look at what does happen, and that's now the beauty of this method. The conventional collocation, which I explained before, where I would brutally discretize and keep my step sizes fixed. I can increase my number of steps, and then as usual, I collect the number of total function evaluations, which I call big M. And what I expect is that my error would decrease with more m. And if I have a higher order method, I would expect this to go down faster. And that's exactly what's happening for our finite elements with switch detection. So it indeed does the trick. On the left, the conventional collocation method really is not doing the job properly. Look at the error here. Even if I have like 200, 300 integrator steps, more or less, my error is still in the order of 100%. No? So this is because this is such a nasty non-smoothness. If I hit the point at the wrong point, I get just a completely wrong solution. So you see that, yeah, you gain a lot. And here, even if you have, for example, this Radau method of 9th order, right? And you do just, what is it, 100? This is about, I think, 90, 80, 70, 60, 50. Yeah, let's say, for example, for 60 points, yeah, 60 integration points, you get an accuracy of 10 to the minus 6. Yeah, very nice, huh? And it's reliable. And you remember we had this discussion, why does it go up at the end? It's because we are at so high accuracies that actually all these methods saturate. And the implicit Euler wouldn't be able to simulate that system. No? So there's really an advantage of doing that discretization. But please keep in mind, in order to solve that simulation task, we had to call an optimization solver, right? Because we use MPCC techniques with a penalty method. But the beauty is now that we can integrate that into an optimization formulation and get everything that we would get with MPCC formulations in general, and additionally the right integration order. So we have an accurate simulation. And here's one of the, I think, showcase problems that Armin worked on. I really like that. The task is actually to just go for a two-dimensional system in a space from this point to that point. And you can control your system by adding, I mean, x dot is equal to u basically. So you can push it, but your u is in a box. Yeah? So it's a 2x2 box. 4 by, I mean, it's plus and minus 2. So you can, and then there's some extra switching dynamics, which isn't visualized nicely yet in this plot, but you should think arrows pointing always here to the center. So basically, depending on your signs of the two states, you get an extra push that's always making you stable in this context. So you're pushed to the center point, but that creates actually interesting sliding modes here between them. And basically the center point is a stable point if you wouldn't control the system. Yeah? So basically you have a constant dynamics pushing you to, in this region, you would be pushed to left bottom, in this region, left up. Yeah? And here on the top left region, you would be going to the right down and so on. And so now what would be the optimal solution is already visualized here, and that is optimized with this method and then formulated as an MPCC and then used with the penalty method. So what you get here is you start with the initial value, which I said is state 2 and 1, right? That's what you do. You go here and you don't have any control. So the control is actually 0 for a long time. So you go until you are on the switch, on the sliding mode. Here's the first switch. Then you're on the sliding mode. And please, this is really like the key, what Armin is proud of. You're staying on the sliding mode and you don't think that you're switching all the time, right? Because that would be, if you're nasty, right? You think, oh, I'm on the boundary, I switch, yeah? No. He doesn't switch because he is now in a different mode. It's just this this behavior where he's here on the switch. So it nicely goes to the origin. In the origin, it stays also for a while. That starts here at time 2. I mean, it's constructed, the example, that's why it looks so easy, but actually the optimizer doesn't know that it switches at 2, right? So now at 2, it just stays there. So until now, there was no control switch on. And then at some point, which is just exactly enough in order to lead you at time 4 to the end, you start to work against your dynamics. And that's at this moment 3 here. You start to push one of the controls, which brings you down. And then you are now on this manifold where your system dynamics would push you upwards, but your control is now stronger and pushes you downwards, but you stay on the manifold. And then at the right moment, your other control is switched on, and then it leads you to the point -1, and you arrive exactly at time 4. So you're lazy, so to say, until the moment that you need to take action, and then you take action. By the way, this is how I unfortunately worked for this workshop. So we knew since a long time that it is happening, and it was like the last 4 days before the workshop that I did my slides. Okay, so I have a suggestion. Maybe people that are more from the, let's say, reinforcement learning community, maybe we could try to make this example into a reinforcement learning example, because it's non-smooth for the dynamics. So this could be a beautiful project, by the way. Just try to address this with a different method, which, I mean, we could do 2 projects, right? One could do it by just smoothing the ODE. What happens if you make it smooth and just don't look at these dynamics? Another one would be to just make, say it's discretized in time, and then I just simulate it accurately, including the switch detection, but I do a machine learning, like reinforcement learning approach on that example, for example. Would be interesting. Of course, even dynamic programming could be applied as a third project. So we could have thousands of projects made around this, if you like, to explore it. I like that example. Good. I should say that with this equilibration, if you don't switch it on with Nurkanov's function, this is just plotted here, but it's not switched on, then you would have a step size which is quite varying here. But if you switch it on, all the step sizes are exactly equilibrated, and they are only changing at the switches, which is what we intended, right? So in that sense, this is doing the job, and we are happy with it. Yeah, there's a question.
There's a question for the chat.
Yes, maybe we stop the recording. Can you do it? And then we do a bit of discussion. Okay, so I want to now to share the idea of time freezing with you. And maybe to start, it's a way to transform a system with jumps into a system which just have switches, which is easier, and which we could treat with these, for example, with the finite elements with switch detection. So if you think at our overview slide again, we are now at this NSD3, non-smooth dynamics of level 3, where we have state-dependent jumps, and we want to treat them with methods that are somehow still based on local optimization and so on. So let's start with an example. So a nice example to imagine is a bouncing ball. Yeah, think of basketball. Here you have a bouncing ball. It has a state of 2 variables. I call them y, it's the height, v is the velocity. Then we have Newton's law, that's just describing the dynamics. And if y is bigger, then Newton's law is just followed, right? So then you're above the ground. But at the moment that you touch the ground, so if the y is 0 at some point, which I call t minus, which is like just before the jump, and if you touch the ground with a negative velocity, so if your velocity is in that direction, at that moment, you just set the new state of v to the negative v. I mean, it's now a positive number again, possibly with only 90% of the original strength, because you lose some energy in this bounce, right? If you look at the time plot of that, then here's this height in blue, it's jumping, right? That's what we thought. But the velocity, which is a state, is just going down until it's hitting the ground, then it's going up 90%, but the other sign goes down because of gravity until it's hitting the ground again and positive. So you see the jumps. And if you plot that in a phase space diagram, then here you have the coordinate to the right and the velocity to the height. And you see that here the state is, so to say, moving down, negative velocities, and then boof, at this moment, you jump here. And then you go on. You hit the switching boundary, you are here, and then you go on. So this is what we see as a simulation. So if you look at this plot, you already get the inspiration for time freezing. What could you do in order to make it a continuous thing? Sorry? X is the whole state, and Q or Y, or QY, I think is in the plot, is the height of the ball, and V is the speed. I'm a bit sorry about the notation. So here I have variables Y and V, and in the plots, in this plot, Y is Y and V. In this plot, it's QY and QV, VQ.
It's moving also like V is decreasing for it.
Why is the V decreasing? Because of this differential equation. Yeah, actually, I think it's really, imagine what really happens if I have my chalk here. I let it fall, zoom, the velocity is increasing, but it's getting negative. That's what's happening here. Thank you for the question. Yeah, but what happens is there is a jump in the velocity, but there's also a forbidden region in state space where we will, that's like under the ground. So what we will use for time freezing is we will actually introduce some dynamics into this under the ground region. That sounds like a nasty simplification, but actually then the other trick is that we switch off time when we are under the ground. That's why we call it time freezing. So there are three ideas. You mimic the state jump by an auxiliary dynamic system on the prohibited region. Yeah, that's the first idea. Second one is we introduce from the beginning a clock state into our dynamic system. We call it T of tau, and this state stops counting when the auxiliary system is active. So at the moment that we are in this auxiliary region, we just don't count time. That's the trick. And then we adapt the speed of time with a positive parameter s, which should be bigger than 1. And that allows us to, so to say, catch up. And we impose a terminal constraint. So we think of constraints here all the time. So why don't we just add a terminal constraint that says this state t at the very end of our horizon should be bigger, should be equal to t. Okay, these are the three ideas, and with them you get the time freezing reformulation, which is absolutely equivalent to the original problem. It's not a simulation, not an approximation, it's a reformulation. So the first step we need to make is that we now say we have an augmented state with one extra state, which we call t now. Yeah, and it's evolving in a new form of time that we call numerical time. That's tau. And then we introduce an augmented system where we have this augmented state, x and t together. They evolve according to the dynamics f and 1. That's if our system is actually in the region where it should be, right? And it has the auxiliary dynamics if you're in the forbidden region, but 0 time evolution. And then we scale this whole thing with s in order to make up for possibly lost time. So that's here the trick. And they evolve with adapted speed. So this is the main idea of time freezing. And obviously this phi is sometimes difficult to find. And there's, let's say, the moment we are trying to find a phi for every possible situation. Yeah? And so far we found one for every idea we had, yeah? Every problem. But obviously it might at some point end. And there's no complete theory of when they will exist and so on. Here, if you get a bit of intuition already, for this point here, you have always these negative speeds will be mapped to positive speeds, right? And a more negative speed will be mapped to a more positive speed. So you see that on topologically, this is possible to be described by a vector field that is like having circles. I mean, we don't care how these circles are. They just need to start at, let's say, 1 and end at 0.9. And the path is a bit arbitrary. And here it looks nice and elegantly, and you can actually even think of these things as spring damper systems. And that's actually how we started the intuition for it. It's like a spring damper system, but you switch off time. That allows you to treat that elegantly. But you could also do very other tricks. And if you increase the state dimension, you could also do really nasty other dynamics, which use switched dynamics to the full extent, even in these prohibited regions. But I will not comment on that. So if you now take the time freezing for the bouncing ball example, so this is just a simulation problem, but how does it work? You would have the numerical time at the bottom, and you have the physical time here. And in this case, we set for simplicity S to 1. So then actually you see that physical time evolves a bit slower than the numerical time, because it's sometimes frozen. And so here you see the evolution of the time state. It's just growing with 1, and then it's not growing, then it's growing with 1, and it's not growing, and so on. Now here you have the numerical time. The numerical time plot of all the state trajectories looks like this. It's nice, continuous. Now you see that it's actually evolving continuously during these virtual time periods, which didn't exist before the time freezing was introduced, right? And then if you now want to plot this, you could just plot the whole system as a x of tau versus t of tau. Yeah? So I just change my x-axis to physical time again, and then I get rid of, so to say, these pieces. Depending on how you formulate your optimal control problem, you need to ensure that obviously these hidden dynamics are not in your objective. But anyway, they would be weighted with 0 because the time is frozen, and so there's no integral objective summed up. So basically, these hidden times, these hidden dynamics, you just forget about them, not only in the plot, but also in the optimization problem. They don't appear. And yeah, now you can use that to do things that you couldn't do before. And here we have a little also academic example, a bouncing ball in 2 dimensions that's driven by a bounded force. So here we have just one 2-dimensional vector q, and its first derivative is a state, q dot. Second derivative is controlled by u. And u is in a circle, so it's bounded. I don't have full force, but I want to track actually a moving point. This is a red point. By moving my ball behind it. It's really a bit invented, but we wanted to have multiple possibilities for switches. So then you are moving inside inside the square, and the square is actually walls on which your ball can bounce or not. So if you move that if your reference point is slowly moving, you would just be able to follow it perfectly. But if it's faster moving, at some point you would have to actually use the bouncing. And the question is, does our optimizer detect this? Let's say creativity that you can gain from bouncing. So if you have a slowly moving reference and you solve the optimal control problem on this horizon of 0 to 4, then you get a nice circular solution here, and nothing really interesting happens. So let's look at this video. This would be, so to say, the true ball following a reference, namely a circularly moving reference, right? With this virtual force that helps to drive. That's simple, just to get the idea. But then you can solve it with a faster reference. So now you want to follow a faster reference, and then it turns out that you need to touch the boundaries from time points. And here left, you have the numerical time plot. Right, it's in physical time. And in physical time, you see there are these jumps in velocities. So how does the plot look like? Yeah, I think we have them both. That's okay. So these are 2 plots. This one is how it looks like in physical time. Yeah, that's a video in physical time. And you see that the ball is actually actively steered against the walls in order to profit from the fact that you get the reflection here. So that's nice. Sometimes it's not. It depends a bit on how far the walls are and so on. And this is the same development in in numerical time. And what you see here is really typical. So you get these 0 time evolution regions. But before and after, you get an acceleration of time in order to make up for it. Yeah? Because our formulation actually keeps the control discretization constant. So the switch can be, there can be a switch or not a switch in a control discretization interval, in one multiple shooting interval. And if there is a switch, there is a part of it time frozen, and then the other part needs to be faster in order to keep the control discretization constant. So also interesting is maybe to look at the first iteration, that's on the left. not yet feasible, but that's with a smaller penalty. And then once you increase the penalty, you get these really more or less exact solutions. Here we use both the time freezing and the finite elements with switch detection together. That's why these solutions are highly accurate. Here you see for slowly moving reference, physical time equals numerical time. But for the faster reference, in the solution, you have these 7 jumps, and at each jump, the time is frozen. And then before and after, you get a bit of acceleration of the speed of time in order to make up for that. There's a question. No, no question. So, second example, unfortunately not yet with the finite elements with switch detection, which we developed only after this. And here it is a hopping robot. You want a robot that's standing on the left at 0. And this robot should just be at 2 at the end of the time horizon. And it should go there with minimal effort. That is actually the square of the joint forces. And it's a relatively small robot, so it just has 1 leg and 1 upper body. But the crucial thing is we initialize it just with standing on the left side. And we just said the objective is be at the end after 2, I think 2 time steps or something like that, and minimize your quadratic effort. And so then you start that whole thing and you let the optimizer work. And at the very end, after the homotopy and so on, you get the solution. And that's for us, this was very exciting because it looks really like a creative solution for this non-smooth dynamic system, just by, so to say, using Newton type optimization and this MPCC penalty method. Maybe if you look at this trajectory in detail, you see that the robot is a bit inaccurately, it's going into the ground. You see, look here. You see, it's not really, and that's because it's not the finite elements with switch detection yet, so it's not as accurate as we like. That will be a next iteration. And I think this is time to stop, so I will not do the 3-step decomposition now, but rather have a bit of time for questions for the time freezing reformulation. So yeah, thank you very much.